Everyone takes a certain path or route to reach a destination. In our current world, many people continue to use map applications such as Waze, Google Maps, and many other applications, especially if these people are unaware of their routes and destinations. However, in situations where people know their routes, such as going back and forth from home to school or to any other destination, most people think that their path taken is the most efficient way. So this leads to the question, how do we determine if the path taken is efficient? Well, according to Lumen Learning, to go through paths efficiently, it is essential to learn the use of Hamiltonian paths and Eulerian paths. Thus, we must first understand the Hamiltonian paths and Eulerian paths to know if the path taken is the most efficient way. Before we discuss about these two, we must first define these important terminologies. In graphing, there are two important terms, which are edges and vertices. Edges are finite set of lines in a graph, while vertices are finite set of points in a graph. Other definitions that are also important are paths and circuits. A path is defined as a walk where all vertices are distinct, while a circuit pertains to a walk that begins and ends at the same vertex, and it does not need to repeat any edges. In real-life applications, the walk being referred into paths and circuits can be roads, bridges, and many other types of routes that are being traveled upon. Speaking about real-life applications, let's give a realistic example. What if you now live in a new community, and you would like to visit all the streets and houses in your new community? What roads would you take first, and how will you go back to your new house? This problem is similar to the Chinese postman problem, where a postman delivers everyone's mail using the shortest possible routes. And to do so, the postman would need to use every route and must return to where he or she started. Now, how can we solve this problem? This is where Eulerian and Hamiltonian graphs come in, where I'll first explain the definitions, the mathematics, and applications of Eulerian graphs and Hamiltonian graphs. Let us first define and discuss Eulerian graphs. Eulerian circuits are circuits that make use of every edge in a graph with no repeats and must begin and end at the same vertex. On the other hand, Eulerian paths are paths that uses every edge in a graph with no repeats and it does not need to return to the starting point. Let's give examples to show a difference between these two. In the first graph on the left, we can see that when we start at any point, it will never go back to the starting point unless it repeats one of the edges. Thus, it is not Eulerian. On the second graph, which is the middle one, when we start at any point, it can always return back to the starting point and it does not need to repeat any of the edges. Therefore, it is an Eulerian circuit, which also means that it is also an Eulerian path. Lastly, on the third graph, when we set this as our starting point, we are able to go through two vertices and edges. However, we are unable to return to the starting point. Thus, this makes it only an Eulerian path. But how can we determine if it is an Eulerian without tracing the graph? To determine, we must first understand the Eulerian theorems and corollaries. Theorem 1. If a graph contains any vertices of odd degree, it is not Eulerian. Theorem 2. A connected graph is Eulerian if and only if all of its vertices are even. Corollary 1. A connected graph is semi-Eulerian if and only if exactly two of its vertices are odd. Now let's take a look at the same examples. In the first graph on the left, it is not Eulerian because it contains 4 odd degree vertices, which is being backed up by Theorem 1. Any vertices of odd degree is not Eulerian. In the second graph, in the middle, it is Eulerian because all of the degree of the vertices are even, which supports Theorem 2. In the third graph, on the right, it is semi-Eulerian because it follows the corollary where there are exactly 2 vertices that are odd. Now for Hamiltonian graphs. Hamiltonian circuits are circuits that visit every vertex once with no repeats and it must begin and end at the same vertex. On the other hand, Hamiltonian paths are paths that visit every vertex once with no repeats and it does not need to return to the starting point. In the first graph on the left, we can see that when we start at any point, it was able to visit every vertex once without repeating any of the vertices. Additionally, it ended at the starting point. Thus, it is a Hamiltonian circuit and path. On the second graph, which is the middle one, When we start at any point, it can go to all of the vertices without repeating any of the vertices, therefore it is not Hamiltonian. Lastly, on the third graph, similar to the first graph, where we were able to satisfy the requirements for it to be a Hamiltonian circuit. Therefore, it is a Hamiltonian circuit and path. Now, how can we determine Hamiltonian graphs? Unlike Eulerian graphs, Hamiltonian graphs are not easily identifiable, but there are theorems that help state that if these graphs are Hamiltonian. There are two theorems that help determine if these graphs are Hamiltonian. The first theorem is Dirac's theorem. Dirac's theorem states that if G is a simple graph of order n, where n is greater than or equal to 3, and if each vertex has a degree greater than or equal to 1/2 of n, then there exists a Hamiltonian cycle. While Orr's theorem states the following: if G is a simple graph of order n, where n is greater than or equal to 3, and if degree v plus degree w greater than or equal to n for each pair of non-adjacent vertices v and w, there exists a Hamiltonian cycle. Note that n is the number of vertices in the graph. Additionally, it is also possible for a graph to be Hamiltonian even if the graph does not satisfy these two theorems, as these two theorems are all sufficient conditions for the existence of a Hamiltonian cycle. Essentially, these two theorems are, even if they do not satisfy the conditions, tells us that the graph may or may not be Hamiltonian. Let's go back to the example and try to identify if it is Hamiltonian through the theorems. In the first graph, since n is the number of vertices in the graph, which in this case is 5, is greater than 3, it satisfies the first condition of Dirac's and Orr's theorem. It also satisfies the second condition of Dirac's theorem, which states that if each vertex has a degree greater than or equal to 1/2 of n, which when substituted, 3 and 4 are greater than 1/2 of 5, or n, which is 2.5. Thus, through Dirac's theorem, it is a Hamiltonian graph. For Orr's theorem, the graph satisfies its second condition, which is the degree of non-adjacent vertices are greater than n. In this case, the 3 and 3 non-adjacent, so 3 plus 3 is greater than or equal to n, which is 5. By simplifying it, 6 is greater than 5, and thus it has also satisfied all of the conditions of Orr's theorem, making it a Hamiltonian graph. In the second graph, it satisfied the first conditions of the theorem. However, in the second conditions of both theorems, it does not satisfy the condition. Thus, it may or may not be Hamiltonian. Through simple tracing, it can be said that this graph is not Hamiltonian. In the last graph, it satisfies the first conditions of the theorem. However, in Orr's theorem, one of the non-adjacent vertices when summed up are 4, which is less than the number of vertices, which is 5. Thus, the last graph does not satisfy the conditions of Orr's theorem. For Dirac's theorem, it also does not satisfy the second condition, as two vertices have a degree of 2, which is less than 1/2 of 5, or n, which is 2.5. Thus, the graph also does not satisfy Dirac's theorem. But even if it does not satisfy the following conditions, the graph may or may not be Hamiltonian. Through the process of tracing, it can be said that the graph is Hamiltonian. To summarize, Eulerian graphs solve the problem of the Chinese Postman problem, as Eulerian graphs require to make use of all of the edges and vertices, while Hamiltonian graphs solve the problem of going through each destination or vertices using certain edges or roads and not repeating the vertices and edges. Now let's go back to the realistic situation mentioned a while back. Let's say you moved into a new community and you want to visit every part of your community. However, you don't want to waste your time and you would want to plan the routes that you would take. What routes will you take and what are the most efficient routes? Note that your starting point is your new house. Let's graph the community. In this case, the vertices are the crossroads, while the edges are the roads that connect to other crossroads. After placing the vertices and connecting them with edges, the graph can be simplified into this figure, making it easier to analyze in terms of Hamiltonian and Eulerian graphs. Let us first see if it is Eulerian. By noting the degrees of each vertex, it can be seen that there are 12 odd vertices. Thus, this graph is not Eulerian. This means that there is no way in going through all the routes and destinations without repeating some of the routes. Modifying the question, let's say you simply would like to visit the destinations and it's not necessary to visit all of the routes. Then, Hamiltonian graphs will be used. By checking through Dirac's theorem, the graph does not satisfy its conditions. Likewise, as shown by the solutions there, by using Orr's theorem, the graph also does not satisfy its conditions. Thus, Through the Drax and Orr's theorem, the graph may or may not be Hamiltonian. By tracing, we are able to realize that it is a Hamiltonian circuit, which means it is also a Hamiltonian path. Overall, now that you've understood the applications of Eulerian and Hamiltonian graphs, you now know the efficient paths to take and planning routes are now easier.